Okay. So with that clarified, I'm going to introduce today's speaker. So Dr. Han Li is a postdoc, a research fellow, research associate in computational fluid dynamics and aeroacoustic of automobile applications at the Ohio State University. So before joining Ohio State, he did his bachelor degree and master degrees in Beihang University, and then he moved to University of Tennessee in Knoxville for his PhD study. He also had a postdoc training in medical research in Duke University. And so his research interests include numerical analysis, CFD structure, dynamics, aeroelasticity, and fluid structure interaction. Recently aeroacoustics and reduced order modeling, high HPC, and CFD in biomedical applications. So with that, let's welcome Han to give this talk, and Han, the floor is yours.
Yeah, thank you very much, Sichuan, for the introduction. And morning, everyone, and very nice to meet you guys over the room today. I would like to share my some of my research. Basically, back in my PhD program on some of my first postdoc during that period. It's about some developments on time domain reduced order methods for aeroelasticity and nonlinear vibrations. So basically today, today I would like to talk about some a brief introduction to the dynamic aeroelasticity. As we, in case some friends here is not that familiar with this topic, and then I'll introduce the first time structure method, basic fundamentals, that is Fourier-based harmonic balance method. And then I will talk about the my branch development of the aeroelastic method based on harmonic balance method. I call it the pseudo time cold coupling aeroelastic approach, which is similar to Sichuan's research. I think he gave a talk in 2020, talk about his time spectra called the coupling approach, but his method is more like the monolithic approach that construct everything into a big matrix and solve it. And my method is falls into the partition category. So I will talk more details about that. And after this method, I also, because the traditional harmonic balance only deal with one base frequency. So how about if there are multiple frequencies? So I also have a development for another method. I call it Supplemental Frequency harmonic balance method for those problems. And also for arbitrary dynamic response that's with no prior knowledge of frequencies. We can also use, similar to the Fourier-based method, we can use the Chebyshev polynomial-based time spectrum actually. So this is what I want to cover today. So first, dynamic aeroelasticity. This is a multidisciplinary problem. It includes aerodynamic force, or in other fluid medium, we can call it just fluid forces with structure, elastic forces, and inertial forces. This is the coupling of those three. So flutter, basically we have two basic phenomena. There we have more other phenomena, but these two are pretty common to this topic. One is called flutter. We usually define it as the onset point of self-excited vibration. So when we look at the figure here, there's a curve defines the stability boundary. So when we move from stable to unstable, at this boundary, it starts vibration, we call it flutter point. And another term is limit cycle oscillation, LCO. Usually in literature, it's defined the vibration following the flutter point that having a finite amplitude. Usually these two terms are used interchangeably, but this is my preferred definition. So from the stability point B move to C, the vibration has a obvious finite amplitude there. So we call it LCO. So at flatter boundary, we can model system by linear method, but for the LCO, nonlinearities are important, and we need some other better approach to model it. So for here, this is example of the DG300 glider. This is a framework. Sorry, this is a pretty popular video that shows the flutter onset. So this speed up. I believe there's another airplane just drag it to speed up, and then after slows down, the flutter stop. Before I talk about my method, I want to talk about some traditional aeroelastic method. Usually, for example, when I construct the problem into aerodynamic part and structure part, so there are the two equations. So usually when we solve the two equations together, we find for example, we just give an input, find a point A, or give another input, we may find point C here. So we gradually try different points, and then finally we can break it and determine this flutter onset point. So this method is based on trial and error basis, and we need multiple rounds of solver. And for the fluid and structure part, we need time synchronization. And so very small time step is required to resolve problem. Another traditional method is called the flutter determinant or eigenvalue method, or just treat it like eigenvalue problem. So this is the structural equation we converted into frequency domain, and for the aerodynamic part, we converted to another matrix vector multiplication by this matrix we already call aerodynamic transform matrix. And then we need to determine this big matrix in left-hand side, and the determinant must be go to 0 for a valid solution of Q. So that's how we can determine a flutter point. Again, this method need to sweep over one parameter, usually the frequencies, and we need multiple rounds of solver. And this method really depends on the number of degree of freedom. I mean, if we have more degree of freedom, we need more rounds to solve the problem. It's the computational cost is basically grows linearly with the number of degree of freedom in your system. So this leads to some questions that we want to improve our approach, and this also leads to some point that we can improve that towards the optimal aeroelastic method. First, the drawbacks to be addressed. First one is if we don't need to run solver multiple times, if we can solve problem in one shot run of convergence, if we can do that, then we can save a lot of computational cost. And then if we can develop method that is the degree of freedom independent, then again, it save a lot of cost. And then if we can desynchronize in physical time between fluid and structure part, and then we can have optimal method for each field. And then it could also potentially improve the efficiency a lot. Also, another point is that if we can solve the flutter and APRC in one solver, it's going to be great. In this way, I developed the one solver method. I mean, based on a harmonic balance approach. So I will talk about how I can achieve all these goals. So the harmonic balance method is a Fourier-based mixed times frequency domain method. So usually a dynamic system, we treated in our research, we frequently encounter a periodic problem. So, but when we do simulation in the periodic problem by using time accurate method, we do have to dampen out the initial transient. It could be long and it could be costly. So instead of going through all this transient and waiting for a periodic pattern to be settled down, we can directly look at this periodic pattern that we don't want to actually go through time step over the period. We just solve some solution at finite, as just a handful of collocation point over a period. And finally, we can resolve every point in between by using the Fourier interpolation. By doing this, we can save the computational cost significantly. And this is inherently convenient to analyze flutter and APRC problem, which is a time periodic. And this method can also easily to model the strong nonlinear periodic problem by using more and more collocation point to resolve the pattern. So this is the example to apply the HME technique to aerodynamic equation. So this is, I just take a Ran's equation as the example. So the uppercase U is dependent variable vector. So we can actually convert it to use discrete Fourier transformation to this into a real and imaginary part. And we assume that we have we need to detain the n number of harmonics. So this leads to a transformation. So the left one is U star is the collocation point over one period, and U hat means the Fourier coefficient. And these two can be converted by just using the Fourier inverse transformation and Fourier transformation. This can be done interchangeably. And then we can substitute this relationship into a Garmin equation. Finally, we got an equation in a number of subtime levels. And this time derived term, look at here. And we can, again, using this relationship here, well, we can replace this with a term that we call the pseudo spectral operator. And when we take our frequency out, the pseudo spectral operator is a constant matrix here, which is very, very nice for a later algorithm development. We can notice that, sorry for my slide. You can notice that from the beginning, we have this equation is unsteady. And finally, when we get the pseudo spectral operator, the equation becomes a steady equation in time. And to easily solve it, we usually, as a common practice in numerical method, we just add a pseudo time derivative here to solve it. But the basic concept is that we use Fourier transformation to convert an unsteady problem into a steady one mathematically. Also, we can do the same thing for structural equation. So this is a general equation, and we can convert it to state space formulation, and did the same thing. Convert it into harmonic mass form with pseudo spectral operator, and then add a pseudo time derivative. One thing I want to mention that we can actually directly from original second time derivative equation into this form. We have a d square omega square here, but this equation is not stable when solved in pseudo time. I have another method to stabilize this equation, but it's not in the main scope of this talk. So I will put a reference in at the end of this talk. So, but at this time, we focus on this equation based on state space formulation. So after this, we can set up an Aeroelastic Garmin equation. So this is fluid dynamics. So this is structural dynamics. We rewrite it into a very brief form. So in fluid dynamics, for example, the Mach number, Reynolds number, usually all these parameters are fixed parameters. And in structure, or the structure property matrix are fixed parameters. So finally, we can give a compact form like this. So everything inside this parentheses variable need to be solved for aeroelastic problem. And in current application, I assume that both flow and structural vibration share the same frequency. That means there's a friction lock-in. So the friction is for the both field. So there's before I talk about my pseudo time code coupling approach, I want to talk about some other established RCO methods. There's this one, I think this is first method of this type developed back in 2002, 2006 by Dr. Jeffrey Thomas from Duke. It treated this unknown vector and just solved this equation by Newton iteration, Newton-Raphson method. But the computational cost scaled linear with number of degree of freedom. So this is not good for our target. Another method I just mentioned is developing my Sichuan. It's similar to the HBRC, but he actually is a non-vector. He also include everything, include not only from structure, also include from the aerodynamics. So it's going to be a very big sparse linear matrix to solve. So another method is to treat it a partition way. So for aerodynamic part, we solved by the HB-CFD solver, and for structure part, we solved by HB formed the structure solver, and then coupled together. So not that actually one time step here, iteration station, we actually marched forward by one time step of pseudo time. So this is the code coupling in pseudo time. Although this code coupling looks pretty simple, there's no inner iteration, looks not a strong coupling, but because it's not coupled in physical time, it's coupled in pseudo time. So it's still stable and good enough for produce a good result. For other two variables, velocity and frequencies, we usually treat it as an input, or we can update by a separate procedure. For example, if frequency is unknown, we can have a frequency search procedure along with the iteration, code coupling iteration to solve the entire system. So this method we cover in pseudo time, and we can let it have a one-shot convergence. And in this way, we don't need the computational cost is nearly independent about the number of degree freedom. This is what we want. So I want to have another detailed explanation about physical time and pseudo time, because this can explain why our one-shot method code coupling is free from time synchronization. So traditionally, when we use the time accurate method, the physical time step is actually very small time step size to resolve the transient. And pseudo time step is an inner iteration at every physical time instance to get that time instance converged locally. But in harmonic based method, the physical time step, because we solve the solution over a collection collocation point, so the physical time step effectively becomes the time interval between this collocation point. They are actually evenly distributed over one period. So it becomes very large compared with time accurate method. And the pseudo time step, instead of the local in a local fashion, the pseudo time step in a harmonic based method, it becomes a global aeroelastic iteration used for this purpose. So they are kind of different. For example, well, if we have flow solver here, we can solve solution over a couple of different points. And for structure solver, usually it's more linear. So we can have less number of collocation points, for example, like this. And then at the interface, when we exchange data between these two fields, we can either use the Fourier interpolation to exchange data without with actually negligible error between this exchange. So that's why when we change convert the physical time step to the time interval of this collocation point by using different collocation point number according to a different nonlinearity, we can let the solver do a code coupling with without time synchronization. So the two solver can take different time step as well as different time integration stream to achieve the fastest convergence rate. So they are coupled, but from numerical method point of view, they are also decoupled. So this is a beautiful thing by coupling in pseudo time. Then there's some other thing about this code coupling approach, also one-shot method. Any numerical method, we need to make sure it's well posed. So there's a unique solution we can determine. Unfortunately, a dynamic error state is usually underdetermined problem because we have safety solver for safety variable, we have structure solver for structure variable, but again, we have two extra unknown that there's no constituted equation. And we need actually to prescribe these two parameter in the equation as inputs. So usually we prescribe the phasal oscillation here. This is an example. This is just a Rayleigh oscillator, very simple example. So, so this is the left figure is a convergent solution, but the right figure is it does not converge if I don't fix the phase, because at the convergence, each degree freedom, it's the phase difference between each degree freedom that matters, not the absolute value of phase. As long the phenomena is going to be the same as long as they keep the same phase difference. So if they don't phase sometime, it's just a shift simultaneous. Every degree freedom shifts simultaneously. The solution does not converge. So the first parameter, I just try to fix the phase of the system. So this is phase shift. We can say before even the converge, there is a phase shift as a transient, and then finally we got a convergent solution. Usually we only need to fix the phase of one degree freedom and correct the rest of one to keep the phase difference updated by numerical scheme unchanged. And this can, by doing this, we can eliminate the side effect. Another parameter we need to prescribe, we need to consider something about this. The one way we can do is prescribe reduced velocity and update frequencies. So this is a typical LCO branch. This is a solution we want to solve. So usually we can prescribe the velocity and then solve the amplitude and update other parameter like frequencies. So what we can do is from structure equation, this is a residual, we can form another equation. So we can take the residual as a object function, and we want to find a frequency that makes the residual to be 0. So this is lead to another updated equation for frequencies. And this way actually works well, but there are some scenarios that make this method less efficient. For example, if we have if the LCO is not subject to stronger nonlinearity, but if the nonlinearity is pretty weak, the curve is actually nearly to a vertical line. So there's a very narrow band of velocity range. Sometimes we cannot actually find the input solution at first to make solver converge. Another scenario is when we encounter an explosive type LCO, and if we prescribe one value here, there's going to be 2 solutions. So the problem is not well posed anymore. And another method is scenario. What about if we want except beside all this point on the curve, if we want to actually solve this point, onset point, so it's hard to find this value at first. So instead of prescribe a reduced velocity, we can actually prescribe amplitude vibration and update the frequency and the velocity together. So by doing this, we actually start from this point, this is input, and then we find this point and frequency. Usually we fix one and we correct amplitude rest of one during iteration to keep the amplitude ratio updated by numerical scheme unchanged to eliminate the side effect. So by doing this, similar to the update frequency, we again use from the residual structure solver, we try to minimize this. We define a object function like this, and we try to minimize this to find these two values to minimize the residual to 0. And these two give us two higher polynomial equations and can be solved easily using a root finding method. So actually, by prescribing amplitude, we can actually solve the flatter point instead in addition to the RCO point. For this part, we can see that if we actually put the amplitude smaller and smaller, the reduced velocity actually getting closer to the onset point. So this is how we determine flatter point in this way. So at flatter point, amplitude is infinitesimally small. This is the definition. And the RCO condition of very small amplitude can be physically interpreted as a flatter point. So that's why we're using the same solver that we can treat the stability problem, which is flat onset, as a response problem, which is RCO. So we solve both flatter and finite amplitude RCO using one solver, using the one method. So finally, this is the flowchart of the one-shot method. So we have two branches. The left black one is the prescribed velocity and update frequencies. The right one with blue flows is the prescribed amplitude and update frequency and velocity. Like any other numerical scheme, we need to know that we need to make sure that the numerical scheme is stable enough to get a stable solution. So for a code coupling approach like aeroelasticity, fluid structure interaction, or any other applications, the point here is energy balance at the interface. So the stability of one-solver method can be done by suppression of the spurious energy generated at the interface. The basic idea is usually over one iteration or coupling, we can say the safety solver, when safety solver much forward, we actually updated the aerodynamic force with fixed displacement. So this zero work is done by flow solver. However, when we march forward the structure solver, is actually the displacement is updated with fixed force, aerodynamic force. So there's some work is done by structure solver. So there's a energy between these two fields is by the numerical method is not balanced. So there's some spurious energy is generated. So by doing this, for stability, we need to make the spurious energies as small as possible. So by how to do that, we can traditionally. So that, well, just let me make our RC pairs here. So traditionally, approach because there's non-zero energy from structural part. So if we want to balance it, we can make energy in the safety part. So that's why that's a lot of aeroelastic method. They instead of going from n to n plus 1, I mean instead of from going one deformation to another structural variable deformation, they actually create a lot of sub-iterations. That means from the update the previous structure variable to the updated one, they create a lot of intermediate values. Try to make the latter safety solver make some energies here to balance here. But the way that the one-shot method is, because the safety solver has 0 energy input, the way here is try to make the energy produced by the structure solver very low. Therefore, it's very low as within the criteria of the stability, and then the whole solver can be stabilized to make a stable solution. So the one-shot method, we directly from one previous update structure variable to the next one, and try to make the energy predictor very low. So we use different energy balance strategies. So by doing this, we need to update the structure equation or solve it by implicit time integration scheme, because explicit cannot fulfill this purpose. For example, here, this is another example from my earlier paper. So this is a pseudo time step and versus artificial energy produced here with different actually iteration numbers. We can see from 100 to 400, we can see the highlight here, the artificial energy actually reduced by an order of 4. So by doing this, the solver can be stabilized. So this is how the one-shot method do the pseudo-time code coupling, and how they can produce all these advantages, and how the solver can be stabilized. The key is using the implicit time integration scheme for a structure solver. So this is first application example. This is 2 degree of freedom pitch plant airfoil. This is supercritical airfoil in transonic flow region. This is one benchmark widely used by aeroelastic field. So this is convergence. So we can see the both structure and flow solver converges simultaneously. And by prescribing different inputs, I can actually resolve this explosive type of RCO. And compare with the traditional HPRCO method, I have the acceleration is obvious. It's much faster than the traditional method. And compare with the time accurate method, you see, we can actually see the CPU time here. Yeah, it's a huge improvement in terms of the computational cost, because we don't care about the transient. We just look into the periodic pattern directly. Another application is another benchmark problem is AGAR 45.6 win. This is the weekend model. And this example at Mach number 1.02772. So again, this is a convergence. Variables here converge simultaneously together. And I also tried to include different normal modes to have a convergence study, but we can see that the convergence rate, the computational cost, is nearly independent of how many normal modes are included in this analysis. And this is the result compared with others. We can see I resolved Father boundary pretty well compared with the other results. And I also did some RCO study by input the amplitude, because you said this is pretty linear here. So I just input amplitude to resolve some RCO curve at different Mach numbers. Again, I compare with the traditional RGB RCO. The computational saving is significant. So this is a one-shot method. So it's basically a Fourier-based partitioned pseudo-time code coupling approach. It has high efficient robustness, and its computational cost is degree of freedom independent. and it's free from time synchronization between two fields, structure and fluid. It makes it very flexible in the implementation of numerical schemes. And it has flexible input. We can input either structure parameter or aerodynamic parameter. And finally, we can solve the whole system. If the frequency is unknown, we have a frequency search procedure to determine it. And we use implicit structure solver to reduce the artificial energy at the interface to stabilize the solver. And actually, it's pretty easy to implement because we can use off-the-shelf standalone CFD and structure solvers. And we don't need dynamic mesh technique. And we don't need to calculate any Jacobian terms. So the whole process from the numerical method point of view is easy to implement. All the thing I just showed here is the method is for system periodic. That means there's one dominant frequencies. But how about if there's a system have multiple dominant frequencies? For example, maybe there's an oscillation from, for example, there's a cylinder vortex-induced vibration. There could be a oscillation with frequency non-locking. So there may be at least two dominant frequencies there. Or for usually come to say in application of turbo machinery, when we try to solve the different flow across multiple cascades, multiple turbine cascades, rotor, stator, because there are different number of blades. So there are different input of frequencies, excitations here. And the traditional single frequency harmonic bands method does not work well for all those problems. So we need to find some other way. There are some papers in the field to deal with similar problem, but I would like to talk about my method because I think my method is much better. Let me put this together. Yeah. So let's do some recap what I just talked about. The nominal harmonic mass method use discrete Fourier transformation. So this is the inverse transformation matrix here. We can see it actually consists of time series and frequency series. This is very beautiful because frequency series is just a base fraction omega, 2 omega, 3 omega. This is the set of the harmonic set. And the time series is actually evenly distributed over one period. So this is a very good formation for this discrete Fourier transformation. This is nominal one. And the stability of the harmonic bands actually depends on the condition number of this matrix. And for this nominal harmonic bands method, the formulation like this one, the condition number, for here I talk about the condition number based on the two norm of matrix. So there are another method to tackle condition number, but this is what I referenced here. So the condition number is 1.0, which is ideal for a stable harmonic band solver as long as the CFL condition for the applied time integration scheme is satisfied. So this is good, the traditional one. And think about that. For when we have a general set of frequency and time instant, for example, there's just an arbitrary set of frequencies here, and the time instant is not evenly distributed. So we have a general form of the transformation matrix. Usually, when the frequency value or subtime levels in this discrete Fourier transformation matrix is deviate from the nominal condition. That means the nominal condition is the frequency is harmonic set, frequency set, time series is evenly distributed over one period. If things changed from this situation, the value of condition number may increase significantly, and then just deteriorate the stability of the harmonic band solver. And such a scenario can encounter when the multiple external frequency coexist in a dynamic system. That's what we just talked about before. A very typical application is turbo machinery. The people how to model it, try to deal with different frequency input. But here, let me just take a simple example. Let's look at the first pitching NAC airfoil, 6-gauge airfoil subject to excitation of 2 frequencies in the invasive transonic flow region. The Mach number for here is 0.796. This case is taken from some other previous aeroelastic case. I just assume that the angle of attack is varied in time according to this equation. So there are 2 frequencies, one omega alpha, alpha A and alpha omega B. For this case, I set omega B to be 2.6. So this is non-dimensional value. And I try to calculate the condition number of that Fourier. If I only formulate this image using these two frequencies, so let's see what happened. So if I fix the omega B to 2.6 and change the value of omega A around 1.0, so see this actually a little bit exchange, it can cause the condition number change dramatically. And for example, if I have omega A to be 10, the condition number is 4.4. 4.4 is not a large value, looks not a large value, but we can see from the right-hand side, this is my residual history. I use different CFL number. If I use very small CFL number to 0.01 for my CFD implementation, it still does not converge. And when I change omega value from 1 to, for example, pi over 3, 1/3 of the pi value is around 1.0472. The condition number increased to 25, around 26. So this is not acceptable at all. So we need to find something other way to deal with this problem. So my approach is, I call it supplemental frequency, because I want to find, because I have 2 input frequencies, so I want to find supplemental frequency to construct a nearly harmonic frequency set, including these 2 input frequencies. The way is, the idea is here, if I can find a base frequencies and I expand it in harmonic series, and this series happen to be that one frequency close to omega A and another close to omega B. So I can replace these 2 frequencies with omega A and omega B. This is 2 input frequencies. Finally, I can have a nearly harmonic frequency array. So the right-hand side is illustration. So I have input omega A, omega B. So I find a base and expand it and replace these 2 frequencies in the set with that is close to input frequencies. So the red frequencies will be used for later analysis. Although it's not perfectly, it's not a perfect harmonic series, but it's a nearly harmonic series. So it still can actually make sure the condition number is small enough to ensure the stability. The base frequency can be determined by sideband theory or using the frequency resource scaling approach, because because I want to save time here. So I won't talk about detail about this thing. I will introduce my paper later on. So this is example. So the left one, So the left one is I found the base frequencies for the case of omega A to be 1/3 of pi and omega B to 0.6. The left one, I found the base frequency from the sideband of these 2 input. So I take this 0.5056 as the base frequency, expand it here. We can see omega 2 and omega 5 need to be replaced. And then I replace this with my input frequencies because they are close. So the condition number from the pure harmonic set 1.0 and is increased to 1.25. It's still good because it's just a little bit increased and the star can be stable. The right table is another try. I use another method called frequency resource scaling approach to find the base frequency is 0.52, very similar. at this case, the omega 5 here is the same as my input. So I only need to replace one of those. By doing this, I increase the condition number only increase very little. It's close to 1. So it's also stable. We can see actually at the convergence, I record the CL here, the lift coefficient. So at the convergence, the primary frequencies dominate Earth energy here. And the supplemental frequencies only have a supportive function. At the convergence, their contribution is close to 0 for here. And also the case here is very, very small. So although the supplemental frequency actually at convergence, they take a little bit energy out, but the primary frequency dominates the result, and we actually recover the physics. So this is one example. This is the result. So first one, I tried different number of frequency modes. They are converged pretty well as an academic example. And and because the period, the time period here depends on the base frequencies. So, and the beautiful thing here for harmonic balance method, we don't need to start from 0 usually. We can start from any time. We can start from 10, 20, or for here, I start from 50. So I start from 50 and try to solve this time period. And we can see actually we can resolve this time accurate, resolve the time response, and it matches time accurate solution very well. And another beautiful thing for this method is that because right now I only resolve this one small period, but I don't need, for other periods, I don't need to rerun solver. I can recover the value at any time instances over the entire time history by doing Fourier interpolation. I can recover every solution here by just from this a few collocation point here. That means for arbitrary, because for this example here, the two frequencies, there's no, there's a irrational ratio. So this is arbitrary vibration. But even for this kind of time dynamics, I can first run a solver by solving this a few collocation point and then recover every solution over the entire time history by doing further interpolation. So this is another beauty of this method. It solves the problem with multiple frequencies, but again, at the same time, it retains the advantages of original nominal harmonic balance method. So one run, every solution here. It's also very easy to implement and for this purpose. So this is period here only for this part. Finally, another thing is that how about if we want to deal with dynamic frequencies, a dynamic response, as we don't know the frequency and we don't know how many frequencies there, we don't know how to update it. So this arbitrary for dynamic response. And the solution that one solution is we can instead of using Fourier series, we can use the Chebyshev series. We can construct a Chebyshev series based time spectral method. It's very similar to a Fourier based one. For example, for the number I collocation point, the truncated Fourier series is like this. And similarly, the Fourier Chebyshev expansion is like this. So they are very, very similar. We both actually convert the solution into different collocation points. And we actually, for the Fourier series, there's Fourier coefficient. And for the Chebyshev expansion, there's a coefficient there as well. It includes, there's a coefficient here, and this is the Chebyshev polynomial of the first kind. And the tau I here is a standard collocation point. It's not a uniform distributed. It's just like a dense, sparse, and then dense again over the period we investigated. This is very similar, and the formulation, the pseudo time spectral matrix is also very similar. So this is the example here, taken from earlier paper. Just talk about the oscillation, rotational oscillation center. We look at the laminar flow the vortex shading behind it. So instead of time accurate solution, we use very thorough step to go through everything. We can actually solve the equation solution at over a collocation point. So the red circle here is the first try. After we got solution, we can start from this point and give it another try. So we can just quickly go over this and resolve the solution. And they also produced a lot of computational savings compared to the time accurate method. This method, this work I done during my PhD program, but I think it can also potentially be used for the code coupling approach and any other dynamic program, dynamic response problem. Oh, so these are some reference. Yeah, I'm sorry, I should actually include more reference according to about the harmonic bands application to the bio-inspired program. I know there are 2 papers, but not many. So all this work I present here is based on my previous work. So these are some reference, and all this work were sponsored by the UNICEF grant number as a grant and a Chancellor's Fellowship at the University of Tennessee when I was a PhD student. So I really appreciate all the support provided. Thank you, everyone. And so the questions.
Yes, thanks, Han, for this very nice presentation. So if you have any question, you can either ask Han directly or you can put that in the chat. So is there any question from the audience? So actually I can start. So so basically for the multiple frequency method, do you see that what if some of the frequency is unknown? Can you do you see that can be applied to those cases?
I mean, the some frequency is unknown, right?
Yeah, so like one or maybe both.
Oh, I'm not quite sure because actually I'm actively trying one case. Yeah, because I'm trying one case is a vertically oscillation cylinder with the vortex shading. So the cylinder oscillation frequency is prescribed, but the vortex shading frequency is unknown.
Right.
It could be Lorcan or Lorcan. But unfortunately, I haven't actually get a successful yet.
I see.
Solution. Yeah, but one thing I think is if it's non-Lorcan case, so the start from cylinder surface to the far field, there is a frequency change because cylinder excitation is one frequency, the overall vortex shading another frequency. There must be a transition zone.
Right.
Flow field.
Yeah.
But only input 2 frequencies there. Maybe that part of flow field cannot be well resolved, and my solver does not converge.
I see. I see.
I can only say there's a potential, but I don't have a definite answer because I haven't actually tried out a successful case yet.
Right. Basically, the phenomenon you describe is that for the PDE solver, for different region of the PDE solver, they have a different frequency for each kind of location, and so it seems really challenging problem to solve.
Yes. Yeah. Actually, from the Dr. Kish, my PhD advisor, he told me there in turbo machinery industry, there's one common problem that sometimes so the cascade always rotor stator.
Right.
So the stator is just fixed there. Yeah. But the rotor, they have to determine if we know the rotation speed of rotor, then it's just the frequency of our inputs. Somehow they want to adjust the speed of one rotor. For example, they want to reduce the chance of the choke or reduce noise or some other purposes. So they need to determine this optimal frequencies.
Okay.
That's another potential field that if there's one frequency and now we can search it based on some object cost function.
I see. Yep.
Yeah. So that's why
application. Yeah.
So, but right now, currently, all this works my side job. So just do it in my spare time. It's not that big progress now.
Yeah, nice.
Mm.
And oh, there's a question from the audience. So it's Cao Linting, I guess, from NWPU. So I'm going to raise a question. So in page 13, why the results have the phase shift when vibration frequency fixed to 1?
Oh, okay.
Do you think it is a physical phenomenon or numerical problem?
I think it's right here, right? Let me just redo the. Yeah. Actually, I put here, I don't think I actually make it clear when I explain this part. I put here to try to see that the importance of the accuracy of frequencies to solve the problem. Why we need another reason why we need a frequency search procedure, because when we have, you see, there are two frequencies, it's 0.997498, which is very close to 1. But this converge, this does not converge. I mean, if the frequency is not at the right accurate value, the solution cannot actually converge. The phase always continues to shift. So yeah, we need to update it to be an accurate value to make sure that the solution converges.
Yeah, the frequency is very important. Yeah, this result I think is very interesting.
Yeah, although for our numeric method, maybe we use different mesh, we use different time integration scheme. The frequency can be shaped a little bit, but for that specific numeric problem here, we need it to be accurate.
Yeah. Okay. So Giacomi raised his hand. Like you want to ask a question? Hello.
Sorry, I wasn't unmuted.
Oh, yeah.
So just to follow up on that point, Hongli, so why is that? Why does your frequency have to be exactly right there? Is that just like a frequency matching criterion that we would normally have for an FFT, or is this something else?
Yes, it's the first thing I want to say is actually when we have a frequency value slightly deviate from a converged solution, the vibration amplitude is about right. It's just the shape, the phase continue to shift, and it's not actually, you see from here, it's just not converted to a steady solution here. And the frequency here is because we do is a flow structure action, the structural fluid, I assume that they are lock-on problem. So the vibration of these two parameters of these two fields, they share the same frequencies. So usually this frequency is unknown. So I just try to update it using that residual-based the cost function. When the frequency is close to the final value, usually when I look at the result, the amplitude of each, for example, each mode or each degree of freedom is about right, but the phase just continues shifting, does not actually stop here.
So let me follow up then. If I may, Xicheng, is that all right? Can I ask another question?
Yeah, sure.
Go ahead. So,
if this were a much simpler problem, not even a fluid flow problem, like a vibration problem, we would adjust the sampling frequency using the Nyquist formula to frequency match the FFT. In your method, is that possible then? Can you somehow adjust your numerics so that the frequencies will match exactly? Or is it because there's a spectrum of frequencies dictated by the physics that, like that would only be possible for one frequency and not for all the ones of interest?
Oh yeah, I think that's that's similar to what just Sachin actually raised up. How about to deal with multiple frequencies? Actually, if I use one shot method, let me show you. Just let me stop share very quick and reshare. There's another example here. I didn't put in this slide, but there's another one. Let me just 1 second, please. So usually, if there's a vibration, for example, there are two frequencies. If it keeps two frequencies there, if it keeps multiple frequencies there all the time, the harmonic balance method will not resolve it because it deals with only one frequency. So that's why I try to develop other methods to deal with multiple frequencies and arbitrary dynamic response. But for some system, initially it has two frequencies, but gradually it becomes one. And if I use harmonic balance method, it just solves that final steady state, does not actually take care of the transient. Let me show you real quick.
Am I missing something here? But I don't think you're sharing your screen anymore. I'm not seeing your slides anymore.
Oh yeah.
Si-Chung, how about you?
Yeah, so I don't share it right now. I try to find something else.
I just wanted Hung Lee to know that.
Yeah, sorry, just for 1 second.
But while you prepare your slide, Hung Lee, I forgot, I wanted to start by congratulating you on a very interesting presentation, and I really appreciate it.
Oh yeah,
nice
thank you
work.
very much. Yeah, I appreciate your kind words. So this is something is not published. So because the case is too similar here. But let me show you something. I tried this on the vortex-induced vibration because there's a non-Lorcan cases over there. So for her, yeah. So here's the example. So for there's a non-Lorcan case, So usually, at first the vibration is like this, and there's for experimental papers they actually also show this kind of result. And if we don't actually look at it for a long period of time, it's just like this. But when we actually let it run, this is time period solution, let it run. Gradually, one frequency will dampen out and another frequency keeps there. From non-Lorcan becomes Lorcan. And when we look at FFT, so there's one frequency just stand here. The energy is not lost. So another frequency just gradually damped out. If I use the one-shot method to solve this one, I can only resolve the final steady state. I cannot actually capture the initial state like this with multiple frequencies because the method itself dealing with one frequency. Yeah. So that's why
I get it. If you slide back to figure 19 there, no, figure 19, I think the spectrum. Yeah. So I think we can agree then the first peak is frequency matched. And so it captured the physics perfectly, but it's not possible to frequency match all the peaks because that second peak that you have expanded as an inset is not a multiple of the first peak.
Yes.
So therefore, obviously you've done a very good job of capturing the second peak, but it won't, I get it. This is the perfect example. This is what I needed to see.
Yeah. So I haven't, because I need to limit the length of slide. I'm sorry about, I need to limit the slide. So I didn't include this case for here because all I showed in my slides is aeroelastic cases. They are frequency locking. And I have another research about vortex-induced vibration of cylinder. There are a lot of frequency non-locking. So if I want to talk about this case, it takes a long time. But this is, I think, I can explain. Because this method only deal with one frequencies, so it just only resolve final steady state. So that's why I try to, this is another case I want to try to solve with the supplemental frequency harmonic bands I developed. And this is also asked by searching that this is known and this is unknown. So I cannot actually search this version so far. So I'm actually working on it right now. Yeah.
谢谢杭里。
Yeah.
你的研究漂亮。
谢谢。It surprised me.
Very nice. Nice.
Very nice.
Yeah. So Zhang Wei asked this question that how do you solve the fluid system for different correlated points? Are they coupled or iteratively?
Let me see. How do you solve fluid system?
So I guess they're coupled.
Oh yeah, I got you. I got what you mean. So they are coupled. Let me show you the equation here. So by converting the original equation into this harmonic bands form, so I solve the solution over these collocation points, and they are each point they are coupled together by this pseudo spectral operator. You see this D matrix here. It's not diagonal matrix. So each collocation point through this term they are coupled together. So it's still coupled. Yeah.
Right.
If it's uncoupled, it's going to be much so easy. So every steady solver can be very, very easily converted on steady solver. But unfortunately, I mean, by nature, it's coupled by this D matrix.
Next question. Johnson from NPU asks that some of the fundamental frequencies are approximated in this approach. So how much influence it will have on the accuracy of this solution?
Yeah, actually, I haven't quantified the accuracy of this solution. I mean, but for my test cases here, they match time accurate solution very well. There's a little bit deviation at the very first. I think it's because integer transient of time accurate solution, but overall it's matched very well. And you just reminded me. There's one thing I forgot to mention about that. There's actually drawback. I need for future research. For this approach, if I want to construct the nearly harmonic frequency set, these two input frequency, if they are very close to each other, then this frequency set will be very, very, there's many frequencies here to be needed. If they are not close to each other, I can have a nice, just a couple of frequencies there. But if they are close to each other, for example, one frequency is 1, another is 1.1, then my base frequency will be 0.1, and they are going to be 10 or 11, 12 frequencies there. If they are even closer, I need more and more frequencies to construct this near harmonic frequency set. So for example, here it's 1 is 1, another is 2.6. They are not close, so I can have 5 just to make it work. So there's another thing, possible drawback I need to study in the future. But overall, this method, this idea should be good. Yeah.
Okay, nice. Is there any more questions from the audience? So if there's no more question, I'm going to stop recording.